V a vector space over a field K. I define this projectivization of V to be basically V modulo the scalars, so V mod 0 modulo the scalars. So I look only on the direction, identify opposite directions as well if you look at R or something, but that's the definition. So in particular, I define the nth projective space over K as the projectivization of K and S1. So, exercise for you. Convince yourselves that first the hyperbolic and parabolic, the projective line over R can be identified with one sphere, projective line over C can be identified with the two spheres. Okay? So consider the action of, say, SL and K, just by multiplying the matrix by a vector. So this action preserves the lines text linearly. So we get an action of SL and K on the suitable projective space. Okay? Now some of these act trivially. Which ones? If I look at the matrix of this form, then its action on x1 to xn is just by lambda x1 lambda xn, which we already identified with our original vector. So this is actually this is the kernel of the action, meaning that anything that acts like the identity must be a scalar matrix, and therefore we define PSL and K to be SL and K modulo the scalars inside of it. And maybe just to mention, this is usually defined, the action we start with is usually with GLN, not with SLN, and still everything works. But there are a few subtle places that even though you model the scalars, PSLN is sometimes not PGLN. For example, for n equals to 2, you don't have equality. Actually, this is a subgroup of PS of index 2, where the index is assigned or something like that. Okay, for what we're going to do today, theorem PS L and K is simple if one of the two things hold, either that n is at least 3, or that n is 2, but K is not the field on 2 elements nor the field on 3 elements. So maybe I should just remark, if I'm not mistaken, that PSL2 F2 is isomorphic to S3, if I recall correctly. I don't remember if it's S3 or alternate group of 3 elements, so I won't make this remark, sorry. But you can compute for n equals 2 and for these field K's the group and show that by hand that it's not simple. And maybe it will be an exercise in the exercise sheet. Okay, so let's start proving this. Please try. Step 1. this is G. So we know that G X here, and we can identify it by G mod Q. Q is the stabilizer. G of 1 point, say the equivalent class of this vector. So you get a matrix. You don't care what happens here, so you have GL2, GN minus 1, and some here. But here you need to send 1 to 0 to some multiple of its. So you get some, I don't know, lambda here and 0 here. Okay? This group is a semi-direct product of U with GLN minus 1. So maybe just an example, or not an example, but if n is 2, then you just get this group. If you check this for n equals 2, you can see that the U is indeed normal in this. That's an example. Okay. So claim, this is something that you're going to prove at home, that the action of G and K is too transitive, meaning that if you take two pairs of different points, then there is a G element which takes one pair to the other. So maybe I'll prove this for n equals 2, which is the easy case, that if I let V and U inside P1K different, and I take these representatives U and V, and I look at the determinant of the matrix whose columns are U and V, then this is non-zero, because U and V are different, meaning that they're not n scalar multiples of each other. So if I now look at the matrix A, whose rows are its determinant inverse times U and V, then A takes 1, 0. That interest U, which is the same as U, some scalar, and it takes 0, 1 to B. So we took a general pair of different points in the space, and we managed to find the map from our specific pair to this pair. Which this implies the transitiveness. Okay, this is one thing, and the second thing that I want to say, so claim, I claim that the action of G projective space is faithful, meaning that it has no kernel. Why? If G and G act like the identity, then it takes 1, 0, some scalar multiple of it. Okay. Certain vector basis, some scalar multiple of it, etc., etc. This must mean that G is of the form lambda 1 to lambda n. But now we look at the action of G on this thing. This needs to be in the same equivalent class as the one vector, but it's lambda 1, lambda n. Meaning that all the lambdas are equivalent, so the matrix to started with should be a scalar, but we already killed the scalars. So the G must be the group identity. Any questions so far? this is something we should keep in the back of our mind. Now take N to be not a trivial group, but some normal group in G. We should show that everything. Okay? So N acts in space, and I claim that it acts transitively. So why is that? So take N is not a trivial group. So there is one orbit at least that that has 2 points because the action is faithful. So consider this orbit and take another orbit. We assume that the action is not transitive, so at least 2 orbits. So if we call this point x, y, z, then we could find the G which takes x to x and y to z. I use the transitiveness here. But that cannot be, because if N is normal in G, then the action of G must preserve the orbit structure of N. Meaning that if x is ny, gx is g y, if x and y, gx is ngy, because n is normal, I can show this, represent it as g times some n1 from n times y. Give it that, sorry. N1 y. So if x is the same in the same orbit as y, gx is in the same orbit as the gy, which cannot happen if we have g which satisfies this. So the action must be transitive as there are no more than one orbit. Okay? Okay, therefore, thus, because this projective space is the same as G mod Q, we have that NQ is Z. Why is that? We have our base point, which is EQ, a viscosity space. And if we take some general point GQ, G mod Q, then transitiveness means we find some N such that N times EQ is NQ is GQ. So G is up to something in Q is the same as N. Okay? So now we start massaging this. Let me move this to this board. So we have this new thing here. You would say, okay, and to say it. So claim that UN is a normal subgroup of G. Maybe you can use that. Let's see why U inside U is normal in G, and let me start again. We have this projection Q on G mod N, right? Because we first embed Q in G in the normal way, and then we divide by N. This is indeed onto because we have this. Okay? Now, U is normal in here. So if we look at the image here, U will be normal again, because this is a suggestion. But now I pull out of my sleeve the fourth isomorphism theorem, or the comparison theorem, something like that. That normal subgroups of G mod H are in one-to-one correspondence with normal groups in G containing H. So if you look in here, then the corresponding normal subgroup of G is NU. Okay? Is it clear? Questions? Please? Okay. So here's an exercise for you, which is useful for now. I define a matrix I naught, E I naught J naught, be the matrix which has one of the diagonals, and another one which is in the I naught row and J naught column. So as an exercise, E I naught J naught, single I naught and J naught, generate G normally, meaning that the minimal normal subgroup which contains this is the entirety of G. So maybe hence, if A sigma is the permutation matrix, corresponds to sigma permutation and elements, then show that A sigma Eij, A sigma inverse is A sigma I sigma J. So this means that if I have this, I can put this extra one everywhere I want. Now show that the set of these generate G by itself. Okay? So what does this mean? I have so now take for example E12, this thing. Then it's new, right? Because look up there, what the form of U is. Okay? This is contained inside NU, which is normal in G. Therefore, the normal closure of it is also inside NU, but it's G. Therefore, NU is G. Now what? Let's take a look for G mod N. N is our normal subgroup. Yes. No, sorry, what you made the remark. Sorry. So your hand waving. So we have N, which is our normal subgroup, and look at G mod N. I want to show that in the end it's trivial. So this is the same as N mod N, but by some another isomorphism theorem, whose number is randomly picked in some manner. This is U modulo the intersection of U mod N. But here is basically the same as the power of K. It's an abelian group. This is abelian. So this is abelian. But that must mean, because we have G mod N being abelian, that N must contain the derived group, which is the commutator group of G with itself. So it's enough to prove now. So claim G is the commutator G with itself. Okay? So if we see that, then any sandwich between two G's must be G itself. Alright, so let's show it. I have another. Okay, Okay, so let me split into cases here to argue in the statement of the theorem. We hope it's here. No, it's not here. It's up there. There are two cases now. N is at least 3, and N is 2 and some demands on K. So let me start with N is at least 3. The idea is basically the same, but computations are a bit different. So this is a calculation one needs to make, and I don't think I'll make it. That if you take E12, take E13, and the commutator, so E23. The commutator is E13. Or maybe this would look more familiar if you know the Heisenberg group. Okay. So in particular, E13 is inside the commutator. But it's a normal subgroup of V, it's a characteristic group. So the normal closure of E13 is contained in it. But it's G. So G is the commutator of G itself. Okay, I can do this. So let's suppose that N is equal to 2 and see some demands pop up on K. So, take some A0 would be general in K and compute this commutator. Then this is another exercise for you to insist, but you can also just believe me. If you get 1, you get here A minus 1, thank you very much, and 1. If we would have known that A squared is not 1, of course that A is non-zero, by varying B, B and K, we find that U12 is inside G from G. So now the same argument is here works. Okay? But how can we make such thing work? If the field K has at least 4 elements, then this is a polynomial. A squared minus 1 equals to 0 has 2 solutions, or most of the solutions are plus and minus 1, and A 0 has 1 solution. In particular, if K has at least 4 elements, I can pick some element of K which does not satisfy this nor this, and I win. So, and yeah. And this is the demand on K. So, maybe a conclusion and then some other stuff time permits. So, the main idea of the theorem is that take any, maybe the main scheme of things, normal subgroup of G is not trivial, then show n extransitively. This. After some nifty algebraic tricks, conclude that G mod n is abelian. Hence, n must contain the commutator of U itself. Then show that G is normally generated by each of those. and argue by cases to show that G is the commutator. So this is the main scheme of things that we're working here if you got mixed with the algebraic stuff in the middle. Okay, so I have, I think, 15 more minutes roughly. Then I want to talk about something else.
Can you just say about SL instead of PSL?
Well, you have this projection, SL and PSL, and then you know it's projected. If you have a normal subgroup here, then its image here is a normal subgroup, so it's nothing. It's contained in the kernel of this projection, which is exactly like scalars. Okay? So, almost. So, for example, if it is S2, the only normal subgroups are everything, nothing, something. Okay.
If G is S3?
Yes. So if S is 3, well, you always have the center in SL and you can't avoid that. Or
If G is S3, then -1 is not an element of SL.
Ah, right. Thank you.
If n is
Odd.
odd, then SLN is simple, and if n is even, then the unique non-trivial subgroup of it is its center, which consists of ±1.
Yes, so write it, it's good. Thank you. Okay, so this goes for that, and maybe I should erase that part instead. So we saw today in class that PSL2 is the free product of C2 and C2 and C3, and there was an exercise to show that if you take the commutator, then it's a copy of the free group from two elements. Okay? This was used by ping pong. Well, this was showed by ping pong. So if you've seen a proof of the Banach-Tarski paradox, you know that usually how do you do this? You take some two crazy elements in SO3, two crazy sets in some space, do some computations, and you deduce that you have a ping pong situation, which is sometimes look very, very weird. Why did these matrices were taken? Where these sets were taken? So I want to give, in the time that I left, some maybe more abstract way to see that you actually have a free group inside SO3. Okay, so the idea is this. Take AB inside PSL2Z, generate a free group. Okay, so choose lifts. Maybe A, B, SL2Z, and the property here is that such that for every word in A and B and their inverses, W is not the trivial element, but also not minus H. Basically because you can project out. Okay? So maybe even SL2R. Okay? So this means that there is a B generate a free group in SL2C. Now, why did I insist on C? We make the following definition. H complex Lie algebra and G side H is a real Lie algebra. G is a real form of H if you have that G that's H that some IH is real Lie algebras. Maybe in a more sophisticated manner, H is exactly the extension of the complexification of C, of D. Okay? So, let me do this. Well, we should make one thing before. If H is a complex Lie group, such as SL2C, and G is, let me write a real Lie group. I mean, a Lie group which has a structure of a real, a Lie subgroup which has a structure of a real Lie group. G inside H is a real form if the corresponding Lie algebras satisfy this relation. Okay? So now here is an exercise which I can solve. That SL2R inside SL2C is a real form. If this is trivial, something which is a bit more sophisticated, but really, if you look at SL2, which is a set of all matrices in SL2C, which are unitary, then this is also a real form. Okay? So, take a polynomial on H in the story. Or think you had in the head if you like, not SL2C. Okay? So, fundamental piece, not its differential is a polynomial small p on a Lie algebra A. Okay? If P vanishes on a claim, if P vanishes on G, P vanishes on H. Okay? So because we know it's already 0 on G, I'm going to look at the derivative and show it's 0. So if I look at the derivative, say the identity, but it goes the same at every point, I have that P inside G is 0. Let me apply an orthogonal element which will make G to go into Alright, just for simplicity of notation. And I now look at the modified polynomial with I need to show now that if P on Rn is 0, then P on Cn is 0. So I only have 5 more minutes, so I won't do this. But this is an exercise as well, sorry. And hint, induction n. This is one way to do this. Okay. Now let me specialize on a very specific form of these polynomials. Namely, stuff of the form word plus or minus identity is 0. Okay? Which is word plus or minus identity. Now, if our group G, which is SU2, does not contain a free group, then for some W, this polynomial vanishes identically. Maybe I should explain why, and it will come later. If this is not the situation, meaning that all polynomials does not vanish identically, then geometrically each of those gives me something of lower dimension. So I have this one, this one, this one, this one, this one, countably many, all of lower dimension. So I can find a point which does not sit in any of them. So the maybe xy, these two elements of G make all these polynomials not vanish simultaneously, meaning that they generate a free group. Okay? But now what? If W is such word, then the exercise implies that W of plus or minus I vanishes identically in group H. But that cannot be because H already contains a free subgroup. So G contains a free subgroup. Actually, a bit more. There are A and C and D in group G such that any word in them, which is non-trivial, not only identity, cannot be equal to identity, but also minus identity. Now let me divide by plus or minus identity. And specialize again on our case of SU2. Okay, so the images here of C and D generate a free group again. But it is well known that SU2 mod of minus I is isomorphic to SO3. So SO3 contains a free subgroup. And you don't need to work any more than that with some crazy numbers and matrices and domains and stuff like that, what you apply the ping-pong lemma on. So again, maybe I should restate the idea here. What I actually showed is that if you have a Lie group, with a complexity group which contains some free group, then any real form of it contains a free subgroup. Okay? Any questions? Okay, thank you. So again, once I open a Dropbox folder, all of this will be uploaded to there, and maybe some more exercises on ping-pong lemmas and stuff like that.